All right, section 4.2, we're going to take a look at prime and composite numbers. So to start with, a few definitions. A prime number is any number with exactly two distinct positive divisors. It can't have three, and it can't have one. Okay, so can you give me a prime number? A number that's divisible by itself and one other thing. How about 3? 3 is divisible by itself. 3 and what other number? 1. Okay, the other number is always 1. Okay, 3 and 1. What's another prime number? 7. Give me one more. 5. I heard 2 of them, so we'll write 2 of them down. 11. There's infinitely many prime numbers. They're not in order now, but that's okay. Right? We've got lots of prime numbers. There's one that's not in your list that's probably worth mentioning. The number 2 is also prime. It's the only even prime number, but it's in the list. It is a prime number. The second definition is composite then. It says any positive integer with more than 2 distinct positive divisors. So can you give me an example of a composite number? 4, 6, 8, about 15. Or 22, right? The list goes on forever too for this list. Do you notice what number's not in either list? 0's not, but 0, we are talking about integers, positive integers. 0's not a positive integer, so we don't kind of have to throw him in there. But you're right, 0's not in either list. There's something else that's not. 1. The number 1 is a positive integer. It is not prime. And it is not composite. Okay, it is not prime and it is not composite. Now, factorization is any expression of a number in factored form. So anytime you take a number and you break it down some way into factors, that is a factorization. Now, if you break it down into prime factors, then it's called a prime factorization. Right? That word's an adjective there. It's describing what kind of factorization. It's one that's primes. So I want to do one example, and then I'll post the videos for the other ones, and you can take a look at more of them for Friday. But we'll do one of them where we have prime factorization, but I want to show you 2 methods for prime factorization when you have a number that's just written out completely. So B and C are different. They're sort of partially factored. Do you see that on B and C on your paper? If you don't have this written down, this is partially factored, and it's partially factored. This one's not at all. Right? So this nuance that I'm going to show you really only applies to this particular type. We can do a factor tree. This is one of them. So you might look at this and say, well, I know it ends in a 0, so it's definitely divisible by 10. And then I'd have 2366. Okay, well 10, it breaks down. It's 2 and 5. 2366. Now you may not know what it divides by, like at first glance, maybe like the 0 ending one. But at the very least, you know it divides by 2 because it ends in an even, right? So even if you get stuck on this particular one, you've got some place to go from here. It will divide by 2. If you divide this by 2, you get 1183. Now, 1183 is not near as friendly because it doesn't end in an even. But that means that you don't have any more 2s. Like as I break this 1183 number down, I won't have any more 2s in the list. But we can add the digits together to see if it's divisible by 3. So if you get 1 plus 1 plus 8 plus 3, what is that? It's 13. It's not divisible by 3, right? So we're just going to go up our list. We don't need to do 4 because if 2 didn't work, 4 is not going to work. Is it divisible by 5? Nope. Now we don't have a 7s test. So if we want to do 7s, we'd either have to do it out by hand, or we would use a calculator, which is fine for what we're doing. That's not our focus right now, is how to divide, okay? So if you divide 1183 by 7, you'll find that it actually does work. And if you divide it, you get 169. And 169 may be a number that you're familiar with. Does anybody know what 169 divides by? Okay, Well, we know it's not going to divide by 2, and we know it's not going to divide by 3, and we know it's not going to divide by 5. We could try 7. If you try 7, it's not going to work. What's the next prime number after 7? 9's not prime because it divides by 3. 11 would be next, right? So does it divide by 11? You'll find it doesn't. 13. This is 13 times 13. So sometimes students will memorize their squared numbers in some class somewhere along the way. So you might have seen 169 before. You might not have, but sometimes that's one of those memorization things that are emphasized in certain curriculums. All right, so our prime factors are all of the primes that are at the end of these tree branches. And we write them with some powers in order. So there's 2 here, so this is 2 squared. There's a 5 here, so it's times 5. There's a 7 here, so it's times 7. And then there's 13s here, and there are 2 of them. Let me show you another way. So trees are fine. The thing you need to be careful about with trees is that you don't simply lose one of the ending pieces of your branches. That's the most common mistake people have when they write down trees, is they might accidentally lose one of them. Trees are nice because they're also very free-flowing. You can choose whatever number works at whatever time you want to do them. There's little structure. So for those of you who are a little bit more free thinkers, you're probably going to like that strategy. You probably know I don't think like that very well. It's probably not a stretch for you to imagine that that's not how I think. This other method, 660, has more structure to it. And what you do is you start by dividing by the smallest prime that there is that divides it. That's a 2. If you do that, you get 11, 8, 30. Well, it divides by 2 again. So then we get 59, 15. Well, 2's didn't work. I would check a 3. 3's not going to work, but a 5 will. If I divide by 5, I get 1183. Doesn't divide by 5, so the next one to test is 7. 7 works. We get 169. And then 169 is 13 times 13. The benefit of this method is that they're all here and they're in order. And I like that. I like order, I like structure. Right? I'm that kind of a thinker. So when I look at this, I can see all the numbers and they go in order for me. So I see 2 squared, and then I see a 5, and then I see a 7, and I see 2 13s. And that's my prime factorization.